Pulsars were first discovered in the late 1960s when their beams of radio emission swept across the field of view of our telescopes and created regular signal spikes, similar to the beam of a lighthouse. Since then, we have discovered thousands of pulsars in our own galaxy, and we have learned that they are neutron stars that are very dense, have strong magnetic fields, and rotate with exceptionally precise timing. But intriguingly, we still don't know what exactly causes the radio emission, partly because there is a lot of variation between the pulsar signals. Hi, my name is Sam McSweeney, a PhD student with CAASTRO at Curtin University. I study the signals from a special class of pulsars that can help us understand this emission mechanism. The classical pulsar model describes the emission that is shooting out from the magnetic poles of a pulsar as a light cone. If this cone was solid and unchanging, the signal would look the same with every rotation. But there is actually structure in the pulse signals which indicates that the beamed emission is not coming from a single, but from several emission regions. The signal that we observe could, for example, be produced by a kind of carousel of subpulsars, rotating at its own speed, in addition to the pulsar rotation. This can explain the stripy pattern in the signal. In this special class of pulsars, we occasionally find a change of the rotation speed of their subpulse carousel. The carousel rotation appears to get faster at some times and slower at others. We used the Murchison Widefield Array, or MWA, in the Western Australian outback to collect data from these pulsars. Operating at low radio frequencies, we have been able to analyze the changes in their rotation speed in great detail. An understanding of the subpulsars might hold the key to figuring out why pulsars give off this radio emission in the first place. One emission model to test is the effect of surface temperature. Patches of charged particles that rotate around magnetic field lines might rotate faster as hotspots on the pulsar surface develop. To cover a large frequency range and simultaneously trace the emission at different distances from the surface of the pulsars, we will combine the data from three telescopes: the MWA, the Giant Meter Wave Radio Telescope in India, and the CSIRO Parkes Radio Telescope in New South Wales.